So Clement's going to be talking about open machine learning frameworks, and we really appreciate him being here.
Thanks. Hi, everybody. Can you hear me? Yes. So the title of this summit is Big Data and Analytics for Financial Services. We have a lot of buzzwords. We could have added data science, maybe machine learning, and we have definitively transitioned to a new era. Some call it the first word of AI, whatever it means. And the interesting thing about this transition is that there has been a variation in the speed of change. More specifically, we can process information way faster. And the thing that I think really interesting is that the information has always been there. The algorithms that we are going to use to process this information are pretty old. The ordinary least square has been introduced by Legendre in 1805. The first neural networks has been built in the 40s. Random forest and gradient boosting introduced as trees at the end of the 50s. And finally, today we have the processing power. We have enough CPU, TPU, and GPU, so a team of 5 can produce the works of thousands. So I'm going to present you how, in this context, we built an open machine learning framework for predictive modeling on financial data. So a few words about my background. I'm a physicist. I have a master in high-energy astrophysics. I have then performed my PhD between France and Spain in nanophysics. I have then joined UC Berkeley, where I have led research at the interface of physics, chemistry, and biology. Things went pretty well there. I have also founded the Berkeley Machine Learning Group, where I was teaching students and faculty how to use data science and machine learning. And more recently, I have joined Credit Karma, where I work in the Wake Ups team as a data scientist. So Credit Karma's mission is to make financial progress possible for everyone. Our 75 million members browse our website or mobile app to obtain financial information. And if they like a product, they can get it, and our partners give us a small fee. That's how we are making our money. This is really nice because it permits us to be and remain always free. It is a platform that will welcome you with grace. I would like to come back with this, but first, the fourth point. We are on the side of our members, partners, and employees. I think that's something pretty important because almost everything that I'm going to tell you can be seen from these 3 different perspectives. For instance, our platform, we're spending a lot of time on the design, so our users are going to have the most enjoyable experience. I don't know if some of you had the chance to pass by our office. It's nearly down the street. It's a really nice space. We really love to have guests around. And if you have a product that can be good for the financial being of people, we have shown, notably with taxes or unclaimed money, that Credit Karma can welcome you and permits you to reach millions of people. And I think it's a pretty strong message to send out there. And finally, Ken, our CEO, treats its employees very well and is a lovely man. So we have a matrix organization. Let's start with the team. The C-level people are in charge of the big picture and they are leading the company forward. Marketing and UX is making sure that the user has the best experience possible. Finance is in charge of how much money is going in and out. Engineering is building the pipes to get the data in. Then BI is going to use this data. Data science is building the models. I am part of the Wake Ups team, meaning that we are in charge of the operation, but we are also making this bridge between data science and business development, who is in charge of our partnership. All these teams are working across different verticals. The most important one is credit card, but we also have personal loan, auto, mortgages, taxes, and education is a very important part at Credit Karma. First, for our members, we want to create quality content so they can understand the complexity of the financial world. And also inside the company, we have this Credit Karma University, where you can learn anything from Bayesian statistics to negotiation. So this is the outline of the talk. I will first give you some context and motivation why we want to build this framework. I will introduce it, and then we will go through a little case study. We're going to try to predict bananas sale. We're going to do some modeling and some forecasting. I will then introduce some practices that have worked well for us at Credit Karma before finishing with some conclusion and openings. So for those who do not know Credit Karma, we are not selling bananas, and the data that I'm going to present here is synthetic. So this is a cartoon of the recommendation system. It is out of the scope of this presentation, but I just wanted to give you a quick overview. Here on the bottom, you have the free platform, desktop, mobile browser, and mobile app that our users are going to use to access the website. At the very top, you have the different data science models that are going to feed them. If you have been on our website, you might recognize what is MyWEC or BestCC. Maybe FFMV2 is more obscure. That's OK. It's just the name of the model. Each data science pipeline is its own ecosystem, which is own content ID and its own rules. And each content is going to compete between each other. And one is going to win for a given user and is going to be served. Then this impression is going to start its life, and it's going to go through a second funnel that we're going to see later. And by the way, the case study that I'm going to present is just one of my side projects. My main job at Credit Karma is to modelize the output of this model upon parameters variation, meaning if one of our partners decides to make it easier for people with a low credit score to get a product, we should show this product more. My job is to quantify how much more we're going to show it and what are the other contents that are going to lose some impression for this product. So we chose to call our framework Mimesis. A lot of companies are branding their framework. You have Airflow, you have Michelangelo, Photon, Mason, Dr. Elephant, who are soon going to run out of particle and animal names. So this has been introduced by Plato in Republic, and it's a threefold reasoning. First, the inmates are seeing the shadows, and they are thinking that the shadows are real. Then they're going to see the fire and the object, and they're going to think that this is the real stuff, before finally getting to the outside world and realizing that the sun is the ultimate source of truth. So this is a threefold reasoning for education and training purposes. You can generalize this to an n-fold purposes. And you can also think that these are not discrete folds, but a continuous process. OK, this is the old way to do things. You're going to go online on your online analytical processing database. Sometimes I would just say online database. You're going to type your query. You're going to get your table. You're going to click on download. You're going to open your CSV file with Excel, do your pivot table, and copy and paste your plot in your presentation. There are several limitations to this framework. The first is Excel itself. You can only process 1 million rows. Then there is a very poor reproducibility, meaning that in the real world, you're going to send a lot of queries that are going to run away for a long time, make a lot of joins. And if you want to reproduce this, you're going to have to send these queries and maybe wait for queries 2C to finish before sending queries 3. And when finally you have your final table, you can start the same process with Excel, meaning that maybe you're going to copy this data, make a pivot table on it, copy and paste them in a different tab. It's going to be very complicated to reproduce this study. For the very same reason, it is very hard to have collaborative working. You have to do the very same thing, but you have to write down instructions for somebody else to repeat this work. And finally, this cannot be deployed. So for this reason, this cannot be the common framework that all the analysts are going to use in your company. So before designing your framework, you need to choose a cloud infrastructure. We are working with the Google Cloud Platform. I have also developed on Amazon Web Service, AWS, and on the Bluemix platform from IBM, so I have some exposure to this platform. And it is clear that AWS is a preferred platform for developers. Airbnb, Comcast, NASA, I think even the CIA is using it. Personally, I prefer GCP for one very simple reason. It's their commitment to the open source, And 3 examples are MapReduce, Apache Beam, and the Kubernetes. And I know that in the worst case, I can always code myself on top of the platform. So AWS and GCP are very good one. You need one to start building your framework. So this is a very simple flow. We are going to use Python, which is, as you may know, a Glue-idle language. Python is going to send a query to your online database, in this case, BigQuery. We're going to use Python again to get the result in a data frame, perform some advanced analytic, some aggregation and modeling, and we're going to output some clean data, a model, and a plot summary. So I would like to give you a few words about BigQuery, and I'm going to give you an example. It's going to be easier. It is likely that in your company, you have one table called revenue, and you have different events with the amount of money that you are generating. And it is also likely that you want to know how much money you're going to make at the end of the month, or let's say 2 weeks after the end of this month, so the data is aged. This is your ultimate source of truth. All your analysts are going to try to predict this number, let's say, 2 weeks in advance or 1 month in advance, and the analyst, which is closer to this ultimate source of truth, becomes a cool kid. I'm going to refer to the data in BigQuery as the raw data, and the data that are being outputted by the framework as the processed data. It needs to be clear to everyone that every data point in your database is heavily processed, and this is not the sun, this is not the source of truth. And if this is your fire, one simple plot or simple table summarizing a complex, nonlinear, at-scale study is what it is, a work of science and art aiming to represent reality. So I'm going to ask for your attention now, because this is the most important slide, and I can prove it to you. Every analyst in your company should be able to interact between your database and your modeling framework. So here we have a very simple send query function, which is going to take a query, sending to your online database, and you're going to get the result back in a data frame. Then you're going to write back some processed data. So that's very important, because it's going to be the core of your modeling framework. So when you come back to your company, I invite you to ask all your analysts and data scientists, how do you pull data into your modeling framework? If they have one line of code, it doesn't matter which language, as long as it is shared by everybody, it is good. If they start going online and opening Excel, that's okay. I'm not fighting Excel, but they should also be proficient using a common framework. If you were to ask me, I would respond, well, it really depends. So here we have BigQuery, which is built on top of Borg, and we have a lot of different methods. We don't have to know them all, but the first one is this user interface where you go online and get the query. The second is a tool called Data Lab. It's a simple Jupyter notebook, if you're familiar with this tool, which is directly connected to BigQuery. I don't really like this because not everybody is using Data Lab, so we have coded our own notebook where you can type the query in the notebook and get the results. And the framework that I'm going to present here is based on the fourth method, so we have one line of code sending the query and getting the results back. So I told you that this send query function should be a very simple function, and it is true, it should be friendly users, but also it should have no limitation in terms of the size of the database that you're going to download, in terms of the speed, in terms of the option. For instance, in BigQuery, you can either use legacy SQL or standard SQL. All of these should be options. So we ended up coding our own version of this function, make it very user-friendly so every analyst can use them. And so that's really important. Make sure that your analyst knows how to pull the data into your modeling framework. So let's start with a case study. Jim is producing fruits. He thinks that they are very good for people, and he would like to use Credit Karma to sell 1,000 bananas, no more than 1,100 and no less than 900. And John thinks that the banana would be great for the members, and so they're going to see what they can do. It's a very summarized story. Usually building a partnership can take up to 6 months. 20 hours on the phone, 500 emails, and we have some guideline to make this kind of partnership. First, the values of the two companies should align. The products should bring something new for the member. We should agree on a fair and sustainable price. And if we agree on all of this, you can go through legal, security, and compliance and have your products on our platform. So this is the real world. You remember the cartoon of the recommendation system? We start here with one impression, and the first thing is someone going to click on this impression? That's the take rate. If they do click, are they going to apply for a credit card? If they do apply, are they going to be accepted? And how much money is it going to generate? For all of these metrics, you have intermediate metrics, and it is very important from the beginning of your study that you are modeling all of those. They are all important for someone in your company, and it's going to be complicated later on to come back and add this to your code. So for our case study, it's going to be a little bit easier. We're just going to have click and conversion, and one metric, the CTC, this click to conversion. So if you were to look at the number of conversion on September 1st, and if you would like to predict how many bananas you're going to sell in September, you would have something like this. Meaning that yesterday, we have almost no trace of conversion because Jim didn't have the time yet to report how many bananas he sold yesterday. So this problem is known as aging. One way to solve it is to wait. If you're looking on the 5th, on the 10th, and on the 14th, you see that we have more and more banana in the database for September 1st. So one interesting thing here is that all these curves are meeting in one point. We're going to call this point the trust date. The trust date is dynamic, meaning that for one content ID, it's going to change in time. It's also heterogeneous, meaning that the trust date is going to be different for different content ID. And I guess it's pretty clear for everyone, but we're going to trust the conversion before the trust date, and we would like to have a model after the trust date that would tell us, at least yesterday, how many bananas did we sell. So do you guys have any idea of what kind of model we could use for this? So I'm going to present a very simple but yet efficient click-to-conversion model. Because we know the clicks for sure, we are getting the clicks, and we would like to know the conversion based on the click. And the hypothesis here is that we have a constant functional relationship between click and conversion. In this case, it is linear. The shape itself doesn't matter as long as the functional relationship is constant over time. Then we're going to choose a learning period. So the learning period starts at the trust date, and we're going to go back in time to learn this relationship. You can see this as a hyperparameter of your system, meaning that if you go back in time for a very long period of time, your predictions are going to be very stable. And if you have a shorter learning period, your prediction is going to be dynamics. So now we have this, we have the trust date, the constant CTC, and the learning period. We can choose a model for this. We are going to choose a very simple ordinary least square, so that when we get the clicks for the past 2 weeks, we can get the number of conversion. So I guess it is pretty clear for everyone why we cannot use ensemble method for this, because if you were to see clicks that were really, really high, this ensemble method, they cannot extrapolate, meaning that the ordinary least square would give you a nice result, while any random forest would give you a plateau. Okay, so here we are. In black, we have the ultimate source of truth, the conversion of bananas, and in green, we have this model. Now, we would like to forecast and know how much banana we're going to sell in the future, and we're going to use some time series for this. We're going to use a tool called the Facebook Prophet, developed by Sean Taylor and Ben Ledam. Keep in mind that you need 5 years of data to forecast 1 year of future data. So this is also a good question to ask to your analyst anytime that you're seeing this forecast. For how long are you training your time series? And on top of this time series, we're going to add some business insight. So we're going to add some training and supervision. Let's look at the plot on the top right. maybe that on the September 18, we have Banana Day. Every year we're sending a lot of email and we know that we are going to sell a lot of bananas. We can go back in time and every year learn the shape of this signal and then predict it in the future. Same thing if you know that your banana lovers are going to be out for a week in vacation and you're going to have less sale. That's something that you can input inside your forecasting. Okay, so here we are. Every day we can have this master conversion composed of the actual, the model, and the time series. And the beauty of the model is that once you have this, you can have this result updated every day. Yes, it's working. So every day when you're going to wake up, you're going to see that the black, the conversion, is going to overlap on the green, and the green is going to overlap on the time series. And you just have to look at this number at the very top, which is your prediction for the month of September. So let's take 15 more seconds to look at this signal and try to pick some of the features of the different models here. I really like this. Okay, let's break it down. On September 1st, the full month of September is just the time series. So you notice that here we didn't put any business inside, it's just the time series. Then we're going to start having the model coming in the September prediction, and we see that on the 15th, we have a big peak of the model itself. It means that we had a peak in the clicks. Then the model is going to learn by itself that it over-predicted this value and going to come back to a more reasonable value. Meaning that we had a CTC that was click-to-conversion that was overestimated. This can happen for a lot of different reasons. One of them is either the product or one email campaign. So meaning that people are going to come on the website because they received an email, but they're not going to transact as much as if they would have come on a regular basis. If our partners are changing their tightening, this could also lead to a change in the CTC. And remember, this is our assumption, a constant CTC. And as the days goes by, that's the thing that I really like with this framework, is that you are sure that you're going to end up converging to the real value, to this ultimate source of truth. It's just a matter of how fast you're going to go there. So you can plot this prediction number every day. And here we can see that we're always below 1100 and always above 900. And we start the month with a 5% error and end up with a 1% error, which is a pretty good forecast for a given product. If you want to get better than this, you need to add business insight. You need to know that there is actually a peak in your conversion which is going to happen, or maybe that the partner is going to change their underwriting, and so this is going to change the baseline. All of this should be included in your forecast if you want to get better than this. Okay, so the problem is solved. We did sell 1,000 bananas for September, but there is more complexity than this. Maybe there is 3 kinds of bananas, the green, the yellow, and the red, and maybe it is very important for Jim to have mostly green bananas. And here on this plot, we see that the mix has changed. So I think that most of you are going to think of this in terms of credit band, and you want to have the best credit band, but it could also be the data science model. And I know that maybe this particular product is performing way better on the green data science model. I don't want to see the red model taking over. So you remember all these metrics that we had at the beginning and that we need to model. We also need to break down each of these metrics into these different buckets along different dimensions. So it starts to be a lot of numbers, and there is no way that you're going to do this with Excel. You need an automated way to perform this kind of computation. So this is a framework that we are going to use. We are going to use GitHub for the control version. And so this code is going to be deployed on the cloud. Here we are using Google Cloud Platform, but you could do the very same thing on EC2. And this is an overview of the GitHub repo. So I think you guys cannot really read all these folders, but The important thing is it should be very well organized, and all your analysts should have the same shape for their repo. The very first folders is called original queries. That's where you're going to store your queries. These can be reused later on for different analysis. You have one folder for the data processed, which is the output, one folder for the raw data, some images that you are going to store, a small description of what the code is actually doing, and obviously the code itself. So once you have this code deployed, we're going to use a very simple technique. We're going to use cron, which is a daemon running processes, jobs, and queries. And so cron is going to ping Linux. We're going to use this code. We're going to use this send query function. You remember that's the most important slide. And we're going to get the data. The data are going to come back to the cloud where we're going to perform some modelization. And then we're going to output some data processed. And if we have heavier data, we're going to store them in the cloud storage. Excuse me. So once we have our data, we now need to make some visualization. You can use some circular plots or chords diagram. This is the very same thing than the cartoon that you have seen at the beginning, meaning that we have our three platforms on the bottom, the desktop, mobile browser, and mobile app. And you have the different data science funnel feeding this diagram. And it's also important to be very consistent in your color code. For instance, if I see something like this, I know that something is wrong because mobile offers is serving desktop, and this should not happen. Some other kind of visualization are the Sankey diagram. They are best when you want to have a visualization of data flowing from one set of layers to one other. For instance, if you want to raise awareness that the CCU, the credit card utilization, should be low, maybe you're going to send a lot of emails, some cards on the web app. You would like to follow the flow of users and see if some of them are going more to this particular place in your website where you are detailing this article on the CCU. It's a very good way to see if you can send a message to your members and this message is being heard and actions are being taken upon this communication. Okay, let's talk a little about time in information processing. You would like to be at this true real time, meaning that you would like to know everything about everyone in real time. Physicists have shown that this is not possible. So we would go to real time. In order to be real time, you need to trigger the data engineering process. That's something that we didn't talk at all during this talk. We have assumed that all the tables are already created in BigQuery. To be real time, you need to trigger the data engineering process, and you're going to encounter a lot of issues. The first is that the data is unconstrained. You have a stream of data. And maybe some events that are going to happen at 8, you're going to receive them at 8:05 or even 10. How are you going to deal with this? So real time is very good for display and inference. Nobody at this point is doing real-time AI or real-time machine learning in production. Some people claim, like at Microsoft with this Brainwave project, that they reached this real-time AI. This is still in the lab. And there is a big leap between real-time and near real-time. So make sure that first you're doing very well at this near real-time before trying to move on to real-time AI. So near real-time is when your process is sync with the data engineering, meaning that all the data engineering is going to create the table and you're going to start analyzing them as soon as it is done. It should be updated every day. Nobody wants to work with yesterday's data. And it is always nice to have two people in charge of the process. So if one is going for holidays or if anything happens, somebody else is here to back up. And finally, you have this Excel time. And it's the same thing. There is a very big leap between near real time and Excel time. So make sure that your company is there before going to the next step on the ladder. Okay, let's talk about the structure of the data science organization. Here on this scale is notably the number of engineers. So when you start with a small team, you usually have a central data science team. meaning that everybody in the company is going to come to this team, and this team is going to respond to everyone. So you have a lot of responsiveness because you're only dealing with one entity. But this can also be seen as all the data scientists looking at only one issue. So when you start to have more and more people, you're going to start to deploy data scientists in different teams. And if you have a manager that understands data science and machine learning, it's going to be okay. If nobody in your team really understands this, it can get a little bit awkward, like this cat on the dog. So make sure that all your managers are really on top of their things on the data science and machine learning before starting to deploy. And finally, if everybody in your company is using the same framework, when the algorithm can be reused for different kind of problems, everybody is pulling with the same convention, then you're starting to have this integrated culture of data science, and that's where you have the most leverage. There are a set of tasks that needs to be accounted for in a data science organization, and usually these tasks fall into 3 different buckets, and usually we have these 3 people, the Chief Data Officer, Head, and VP of Data Science. So these are vague guidelines, and some companies do very well without these people, but you need to make sure that this is accounted for. So the CDO is in charge of the organization and the leadership. He's part of the EC committee, and is showing consistency over time. That's the person that you are going to trust, is designing the framework, the metrics, and giving this at our fingerprint data access, meaning that everybody is in EC knows where to find the banana forecast. Sometimes is in charge of security, which should be the top and only priority in your company. And sometimes you even have a chief security officer, that's also fine. Is also the person who's going to choose if we're going to build a product in-house, if we're going to partner with somebody else, or if we're going to buy a startup and acquire somebody else to produce a new product. The head of data science is a researcher, is a scientist. He's publishing in machine learning journals, he's formulating the problem, he knows the algorithm very well, he's active and pushing in the GitHub repo, is the guidance for the junior scientist, and is the one building the core of the framework. Finally, you have a VP of data science, which is more a connector and a manager. So it's going to connect the team and networks together. He's a central repository for ideas. He knows the people very well. He's also doing this at our fingerprints data access, but here this is for the analyst and the data scientist. So he's the one who's going to know that we're going to send an email and that we should incorporate this in the framework. He's the one who's going to build the team, recruit, and retain people in the companies. I have seen this poll recently, and I don't know how accurate it is, but it seems that people are staying on average 2 years in the Bay, in data science company, and I have been amazed in this because you're going to invest a lot in employees, and they're going to switch every 2 years from Amazon to Facebook to Microsoft to Google. So that's a real issue, and you need to have a strategy. You have 2 options. The first is to try to retain your employees, or the second is to invest heavily in the recruiting process and make sure that everybody is using a common framework so that one person is creating one particular metrics for your company, which is very important. If this person leaves, you don't want to have a gap of 1 week trying to understand all of these queries, all of this process in Excel. It should already be there. Or worst case, you should just have to run prediction and get the results. Okay. So we're getting towards the end of this talk. The main takeaways. You need to make sure that every analyst in your company can interact between your database and your modeling framework. Use some crisp SQL, some simple modeling and beautiful visualization. Make sure that you have a framework which is replicable, collaborative, organized, and up-to-date. And remember this best practice, and everything should be okay. I told you at the very beginning of this talk that Credit Karma's mission is to make financial progress possible for everyone, and that's something that I truly believe in. I wake up every morning, I go to work, and I do as much as I can to make this happen, but the complexity of the problem the amount of data that we are ingesting every minute makes it very challenging. And the information is out there. We have the pipes. We have the computing power. The time has come for everybody who believes in this financial progress for all to team up so that we can channel this information to the people. How we are going to do this, I do not know the details yet. It needs to be very transparent, very secure, sustainable. I don't know which algorithm we are going to use. We have all these random forest, gradient boosting, deep learning, and those are amazing. Success stories come in buckets using predictive modeling. But they are also very isolated algorithms. And the interesting thing is we have seen this before. I also told you at the very beginning of this talk that by the end of the 19th century, we had all these amazing techniques, such as this ordinary least square, the Dirichlet process, all these analyses that exist as separated entities. And as it is explained in their book, Computer in the Age of Statistical Inference by Asti and Efron, a small but significant step forward was an argument between Eddington and Fisher about whether the absolute mean or the root mean square was a better estimate of a deviation from a normal sample. So Fisher won this argument. And not only he has shown that the root mean square was better, but he has shown that it was optimal. Optimal is a key word here. Before Fisher, nobody really understood what estimation was. The same thing can be said today about predictive modeling. And it is possible that there is some information out there that would permit us to unify the field of predictive modeling as it has been done with statistics. It is likely that the person who's going to do this is not in this room. We're coming a little bit late for this. But our jobs as scientists, engineers, and leaders is to build this kind of open framework, to support research, to teach in our own company or in universities to pave the road so that the next generation can break through. Thanks for listening.
Q&A. Who has some questions for Dr. Rydell?
This is a simple question, but you showed a couple slides that spoke to having the recommender systems based off the channels. I was just wondering why you would have different models across the different channels. So you have your mobile and is it truly the type of customer that is going to theirs is different, or is that your real estate on the device changes it, or why would you have so many different models with only 3 different channels?
That's a very good question. Why do we have different models? So first thing, I want to be very honest with you. Everything which is presented here or everything which is released as open source is outdated. So we have moved away from this. So we need to have these different models because if you're going to serve best CC, this should be the best credit card for some person. It has some legal implication. So maybe the best CC cannot be CPA, so cost per acquisition driven. It should only be for the users. So this should be a different kind of rules than the card that you're going to see when you're going to see the dashboard on the website. And we need to account for these different rules for the different placement on our website.
Did you have a question?
I think you mentioned it. Doing reproducible research is often a big challenge. Be it that you 6 months later you go back and code doesn't even run because the libraries you use have changed, or it gives a different result because your SQL had a date greater than rather than a date between or something like that. How do you work on making that the research that gets checked into that the Git repo that you demonstrated is reproducible?
So that's also a very good question about reproducibility, and above this, about this unique source of truth. And it is true that maybe even your data is going to change in your database because your data is going to age or maybe something is going to change in the way that people are reporting. So the answer is really this framework. If you have a code which is deployed and which is producing the same output every day, at least you know that your methodology is not going to change. So that's a very big leap forward compared to I'm going to rebuild the same analysis from scratch, because we know that we have a lot of possible source of errors during this analysis. So my answer would be, and yes, so this is a representation of a very, very complex truth. So it's going to change. Make sure that you have a common framework and that you are outputting the same value every day, and see the variation in this value to make sure that your results are actually reproducible.
Can you comment on how do you balance the objective function to your end users and the banks and credit card companies you're trying to recommend the business in the data fitting?
Exactly. So we have 3 different components for these objective functions. The first is for our members. We want to make sure that we're going to serve them a product that they're going to be approved and that is going to be good for them. The second is for our partners. So when I have joined Credit Karma, I have been told that we don't have any hard commitment. I have then realized that the truth is a little bit different. We really care about each of our partners, so we want to make sure that when we're going to make a deal, we're going to be able to deliver what we have agreed upon. And the last one is for the company. So it should make money for us. So these are the 3 components that are in our objective function.
What's the outcome data you use to train the models? So for credit scoring, right, it's the default data is the outcome. So in your building the model, what are the outcomes that you're trying to build a model fit those outcomes?
Okay, so before the outcome, I'm going to tell you what is the income. It's the traffic that we are getting in every day. So a lot of people are coming to the website, and we have a lot of features that we know about these people, and we're going to try to predict whether or not an offer is going to be good for them, meaning are they going to be approved for this particular offer, and that's one of the outcomes on the user side. So the outcome of the model would be one number that summarizes the likelihood of someone being accepted for the offer, how good it's going to be for the banks, and how good it's going to be for our company.
I'm trying to work this. Following up on what you just said, when do you look at different data such as age and education and such to predict what that particular consumer might want in 3 or 4 years in terms of credit cards and such? Do you have models that do that?
In 3 or 4 years?
Or in 10 years or 40 years or whatever?
So it is really complicated. We are definitively making studies and that takes into account the variation of the score upon the next years and what are the parameters that are important in one user's having its score going up, staying stable or down. And there are like a lot of different profiles. So people can have a linear profile. They can have some setback, meaning that there is one event that is going to bring their score down and then they're going to come back from this. Some of them are going up and down all over the place. So we are predicting this kind of behavior, but that's not really getting directly into our model. It is more on the quantitative research side.
Any last questions for Dr. Rydell? Going once, going twice. He's smarter than all of us put together. This is your big chance. All right, thank you, sir.